Good morning, children. Here are some extra questions based on this alpha, beta, and gamma emission. How the nucleus changes and what new nuclei are formed when alpha, beta, or gamma are emitted. So these are a little more complicated ones. So they have given 1 beta, then gamma, alpha, beta, and they've asked you to complete the following. So in this case, they have just given X, A, Z. That means you have to keep it as general. Specific values are not given. Okay. So if you want to do it continuously, or you can do step by step also. So X, A, Z, when it gives beta, it becomes, so you know beta will be 0 minus 1. So what will happen to x1? Its atomic mass number will remain the same. Atomic number add 1, minus of minus 1 plus 1. Okay, then this is giving gamma radiation. Okay, so that means it was in an excited state. Just put a star kind of a thing, and then A Z plus 1, it is giving a gamma radiation. You know, gamma will not alter the mass number and atomic number. So X2 will also have the same mass number and atomic number. Then coming to the next one. Now X2 gives alpha. So X2 A Z plus 1 gives alpha. That means alpha 4 2. That will be X3 A minus 4. Okay, A minus 4. Then Z plus 1 minus 2. Z plus 1 minus 2. That will be Z minus 1. Z minus 1. Okay, so then X3 A minus 4 Z minus 1 gives a beta particle. So a beta 0 minus 1 plus X4 will be A minus 4, mass number will remain the same, atomic number Z minus 1 plus 1. So these two will get cut. So you'll have A minus 4 and Z. So finally what you should do, you have to fill this up. If you want, if you can do it directly also, it's fine. Okay, otherwise finally you fill this up. X2 will be AZ plus 1, X3 will be A minus 4 Z minus 1, and X4 will be A minus 4 and Z. Okay, so this is the solution. Okay, this is the answer. Complete the following they've asked, means they basically asked you to fill the atomic number and mass number and atomic number. Is it clear, children? Hope you have understood it. Now we'll go to the second one, where they have given the mass number and atomic number of the final nuclei after undergoing so many disintegrations, and then they've asked you to find and they've asked you to complete this. In the sense, you're asked to fill this mass number at X, X1, X2, X3 ka mass number and atomic number. Okay, so same way you start with AZ. Okay, now I'm going to do directly, children. Okay, I'm not going to do stepwise, so you can do it like this if you don't understand. Otherwise I'm going to do, so if it emits alpha, so it will become A minus 4 and this will become Z minus 2. Then if it emits gamma, means it was in an excited state, and then its mass number and atomic number will remain the same. Then it's emitting beta, mass number won't change, atomic number increases by 1, that is minus 1, that is Z minus 1. Then it is giving one alpha. So this is what is given. Okay, X4 A minus 4 minus 4. Okay, you leave this for a while. You just keep doing the general thing what you're doing. Okay, X3 A minus 4 Z minus 1. When it gives alpha, it becomes X4 A minus 4 minus 4, and when it alpha atomic number, subtract by 2. For mass number, subtract by 4, so minus 4, and for atomic number, subtract by 2. Now what you do, you can equate this and this and this and this, because x4, both are x4, and so 206 will be a minus 8. Okay, minus 4 minus 4, 8. So a will be 206 plus 8, that will be 214. Then b, z minus 3, this is z minus 3 is equal to 82. So z will be 82 plus 3, that is 85. Okay, now after finding a and z, again you have to fill them. Don't leave it like this. You have to fill them in terms of a and z. Don't leave it generally. In this case, it was only general. They didn't have any specific number, so you left it like that. Now, in this case, because there was a specific value given, you have to get back and then write it again. X, A, Z. So, A is 214, Z is 85. And then gives alpha will become x1 will become 210 and 83. This will become, give gamma, that will become 210, 83. Then it gives a beta and becomes x3. No change in mass number. Atomic number added by 1 gives alpha x4. Then you get this one. Finally, we'll have 206 and 82. Is it clear, children? This is the solution of this sum. Complete the following they've asked. This is how it has to be solved. Hope you got it. Okay. So now there's one more sum which is of a little different type. Uranium nucleus uranium-238-92 undergoes several disintegration. Okay, you don't know 1 alpha, 2 beta, 2 alpha, 1 beta, alpha, beta, then alpha. We don't know. Okay, it is just undergoing several disintegrations. Only that much is given. And ultimately decays to lead nucleus. Okay, Pb20682. How many alpha and beta particles are emitted? How many alpha and beta particles are emitted? Now, uranium-238-92, it is disintegrating. You don't know how many times. Okay, it emitted alpha and beta. We don't know. And finally, okay, there will be so many steps. And finally, it became lead 20682. 20682. Now, how to solve this? Okay, what you do, so this gives Pb20682. So definitely there will be some alpha and there are going to be some beta. Okay, we don't know. So let's take X alpha and Y beta. Okay, you can take as X alpha particles and Y number of beta particles are emitted. So now let's form an equation to conserve the mass number. So 238 is equal to 206 plus x into 4, that is 4x, y into 0 is 0. So 238 minus 206 is equal to 4x. 4x is equal to 32. X is equal to 32 by 4, that is 8. Can you understand? So 8 alpha particles has been emitted. Come to the atomic number. 92 on the left hand side is equal to 82 plus x into 2, that is 2x, plus y into minus 1, that is minus y. Did you understand this, children? When we see the atomic number, okay, apply the law of conservation of atomic number. 92 left hand side 1 equal to 82 plus x into 2, that is 2x, y into minus 1, that is minus y. Now let's solve it. 92 minus 82 is equal to x value you have already found, so you can put that 2 into 8 minus y. Bring y this side. 2 8s are 16. This is 10. Okay, so 6 y will be equal to 6. So number of alpha particles emitted were 8 and number of beta particles were 6. 6. Is it clear, children? So this is the answer for this kind of sum. Okay, so you just write x alpha, y beta, then form equations and then solve it, you will get the answer. Okay, these three are little complicated ones, so I thought of doing it in this video. Okay, now come to the last part of this chapter and then the last part of your syllabus also, that is, okay, I don't know, I think I told you, no, this part is cancelled. Nuclear fission fusion is being cancelled from your syllabus. Okay, so what we're going to do now is the last part of this chapter, that is uses of radioactivity. Uses of radioactivity or radioisotopes. Okay, now you know that which elements are supposed to be radioactive. Now we saw generally here isotopes of nearly all elements of atomic number higher than 82, they are naturally radioactive. Okay, but the isotopes of some elements even with atomic number less than 82, they are also found to be radioactive and they are called radioisotopes. Can you understand? Few of them, they are exceptions. Even their atomic number less than 82, but still they are radioactive. They are called as radioisotopes. So what are radioisotopes? This is the definition. Okay. And then another, they've given some examples like cobalt and all. See, it's 27. Atomic number is only 27, but still it's radioactive. When carbon 14-6 is radioactive. Potassium is radioactive. Phosphorus is radioactive. These are all called radioisotopes. Okay, you can study some examples also. Cobalt, carbon 14-6, these are some radioisotopes. Okay, now there's another term called nuclear transmutation. Now these radioisotopes sometimes are naturally prepared. Naturally, sometimes they have the radioactive emission. They can also be prepared artificially. That process is called nuclear transmutation. Nuclear transmutation. That means, so what is nuclear transmutation? It is a method of preparing radioisotopes artificially. Okay, artificially in the lab they will prepare, but all that they have to do is make some changes in the nucleus. Okay, by changing some number of protons and neutrons, it will become radioactive. So this method involves changing the nucleus of an atom artificially to produce radioisotopes. That is called nuclear transmutation. Okay, mutation is variation, you know that, right? So that is, so you can just note down this, it's not given clearly, this one. Okay, now the uses have been divided into three categories: medical use, scientific use, and industrial use. Okay, we'll go one by one. Medical use. Many diseases like leukemia, cancer, etc. are cured by radiotherapy using gamma radiations from cobalt 60. Now, one thing is gamma radiations are very, very immense damage. They can cause immense damage. If you expose your body to gamma radiation, the skin gets just burnt off, okay, because they're so powerful. But they can also be used for this useful purpose. Suppose if there are some cancer cells here, to kill those cancer cells, they use these gamma radiations to fall on those, and that will destroy these cancer cells. You know what is cancer cell, no? Fast multiplying cells. So they have to be killed, and they have to be shrunk before they are removed using surgery. So to do all that, they do something called radiotherapy. Okay, leukemia is blood cancer, and other cancer, any cancer. And what do they use? Gamma radiations from cobalt 60. Gamma radiations from cobalt 60. That is the first use. Second one, there is another type of radioisotopes called tracers. Tracers. What are tracers? That could be Another question here. The salts of weak radioactive isotopes such as radiosodium chloride, radioiron, radioiodine are used for diagnosis. Now this is for treatment, killing cancer cells. Diagnosis means for finding out whether there is a tumor, or diagnosis purpose, you understand, to find out what the actual problem is. You have severe headache for so many days and you go to the doctor, they have to do a diagnosis, they have to do a series of diagnosis. That is called diagnosis, to find out what is the actual problem. For that they use some weak radioactive isotopes, weak radioactive isotopes like radiosodium chloride, radioiron. These are called traces. Now what do they use it for? Second use. So first use you can write the one. Second use, tracers are used to detect the suspected brain tumors and blood clots before they become dangerous. Okay, any tumor in the brain or any blood clot can be diagnosed with that. The third use, if you're really interested in all this, please go through this and you will understand it much better. But okay, yeah. Gamma rays. Third use of gamma rays are used to sterilize bandages, dressing syringes, and other equipments made to make them free of germs. Okay, you know what is sterilization? Okay, so before putting bandage, you have an injury or somewhere, the bandage has to be sterilized, made sure it is completely free from germs. Even gamma ray, they allow gamma rays to pass through them to make them sterilized. Okay, those three are the medical uses. And why do they use this? This method is quicker, more reliable, and cheaper than sterilization by heat. Okay, fine. Scientific use. Okay, these terms might be little different for you, but just keep understanding and going. Okay, alpha particles emitted from radioisotopes are used as projectiles for nuclear reactions. Okay, so nuclear reactions, to start even a nuclear reaction, okay, so sometimes they are used. Then the second one, radioactive tracers are used in agricultural science to study the growth of plants by using a particular chemical manure. Okay, so tracers are used to study the growth of plants by using a particular manure. Okay, the third is a very important use called carbon dating. Have you heard this term, carbon dating? What is carbon dating? Okay, it is the process of finding. Now you find a very old trunk, okay, a tree trunk. The tree has been cut, the trunk is there, okay. You know that it's a very old trunk and you're interested to know how old this tree is. How old this tree is. You know, there is a method to find, that is called carbon dating. The method to find the age of this old tree trunks or trees or rocks, they're found using this phenomena called carbon dating. Carbon dating, what do they do is, okay, in this phenomena, so you have, this is what is carbon dating. If they ask, this is the answer. Age of rocks and of buried plants is estimated by the study of rate of decay of carbon 14. They all have, trees, rocks and all have some amount of carbon when they were formed. Depending on how much carbon has been emitted, how much carbon is there right now, they can decide how many would have been there, and that means that is how many years back. Okay, so if you're really interested, please go into it and study in detail. I'm not going to go into the detail, but just that you know what is carbon dating, and it is done with the help of by studying the rate of decay of carbon 14 by beta emission in the remains of, they'll see how many the rock is emitting, how many beta particles placed. Based on that, they will track back how many years back that plant has started living. Okay, then comes the industrial use. Okay, industrial use, radioisotopes are also used as fuel for atomic energy reactors. You know, nuclear fusion, nuclear fission, for all that, sorry, not fusion, fission, they use uranium as the fuel, and that is radioisotope. Then they are used by engineers in factories to avoid accumulation of charge on moving parts of machines due to friction. Third interesting uses, they are used to make certain luminescent signs. I think you would have heard about these radium dials and some clocks. On the needles there will be a radium radium material on it that even in the night when everything is switched off, that will glow. Okay, that is, radium is a radioactive material. Okay, and that is one of the use. They can glow even in dark. When there is no light, they still can glow. Okay, that is one of the use. Another use is to control the thickness of paper, plastic and metal sheets. You know the penetrating power, yeah, we studied. Based using that, they can control the thickness of paper, plastic and metal sheets during their manufacturing process. Okay, now the next is sources of harmful radiation. Now as such, this topic is not there. Now basically, from where do you get all this harmful radiations? Mainly from nuclear power plants. You just know the heading, that is enough. Nuclear waste. Okay, nuclear power plants, after using that uranium, okay, even though it is used, it will have still some radioactive, it will still be radioactive. Then where do they dump it? And even if they dump it somewhere, it keeps emitting radioactive rays. Other sources like cosmic radiation and x-rays. Okay, so just have an idea about it. The next important thing is harmful effect of radiation. What are the various harmful effect of radioactive radiation? Again, there are three main topics. There are three main effects. One is biological effect, means it affects your body, and that can be short-term recoverable effect like diarrhea or sore throat or loss of hair or nausea. Okay, this is short-term. You can get recovered. Most of the times it is long-term irrecoverable effect like leukemia and cancer. So you know that during World War, the atom bomb that was used in Nagasaki and Hiroshima and Nagasaki, and the radiations that were emitted, even people now have been affected by cancer and all that. Okay, because it causes long-term irrecoverable effect. Genetic effects also, it can cause genetic effects. That means it can pass to from one generation to another. That's what has happened. Okay, it happened so many years back, but even the younger generation have been affected by that, and they have some defects in their bodies or some kind of problems because of the radiations to which their grandparents were exposed to. So these are the possible biological effect. Okay, the first and second type are limited to the individuals who are actually exposed, well, the third type affects the later generation, which is very, very dangerous, of the person exposed to the radiation. The genes get modified, mutated. Okay, the second harmful effect could be the exposure of pregnant women to X-rays for a long time may affect the child in the womb. Okay, so this is another harmful effect. Third one, exposure to gamma rays destroys the cells of body and affects the blood cells, gastrointestinal tract, reproductive and hair cells. Exposure to gamma rays. This is X-ray, this is gamma ray. Here I told gamma rays have some positive use. They are used to treat cancer. But you should understand this, children. Now suppose, for example, let me take my hand. Okay, this part has some cancer. Okay, there are some cancerous cells here, and they are to kill those cancerous cells, they are sending some gamma radiation. Okay, now maybe only this much area will be cancerous. Only this much area will be cancerous. These are normal cells. These are only fast multiplying cancerous cells. Only I want to destroy them. But what will happen when gamma radiations are made to fall on them? It's not that only exactly this much will only get exposed. Even this nearby cells also get exposed. In fact, even the whole area might get exposed to gamma radiation. And you know what will happen? These good cells or the proper cells, they also get damaged, and it can cause so much pain. Okay, there are two things they do for cancer treatment. One is chemotherapy. For those of you who have had cancer patients in your family, you know. Other one is radiotherapy. Okay, so radiotherapy means they'll expose the cancer cells to gamma radiation. So when they do that, even the nearby good cells also get affected. If it's a stomach cancer, you can imagine they'll expose a particular part, but the nearby, even the entire gastrointestinal part will track will get affected, and these people will have severe problem in eating. They cannot eat. They'll be in so much pain. These two are very painful processes because the after effects are so much, and even they lose their hair. You would have seen sometimes cancer patients, because it will sometimes kill the good cells also. They lose their hair, their skin becomes black, they have constant vomiting and all that. Okay, these are the effect of gamma radiations. Though it is used to destroy these bad cells, it can also destroy some good cells, but there is no other option, because these cells have to be destroyed, otherwise that's going to be too dangerous for your body. Okay, so this is how, here you saw it as use gamma radiation, and here you're seeing it as harmful effect, but both might take place. Okay, safety precautions. This is the next topic. Safety precautions, uses, harmful effects, and safety precautions. These are the three topics. Okay, now there are, again, they have given in three headings. I've marked all the important safety precautions. Okay, during construction, while constructing a nuclear power plant, they have to take some precautions. While handling the radioactive material, they have to take some precautions, and then while disposing nuclear waste, they have to take some precautions. So they have given stepwise. I've just marked the important ones. First one, nuclear reactor of power plant must be shielded with lead and steel walls so as to stop radiations. One thing you should know, lead is one material that can stop the radioactive radiation. Suppose there is a nuclear power plant here, there is lots of uranium here. Okay, there will be control rods and all that, and they are constantly emitting alpha, beta, and gamma. So this container, this one, they make it out of lead or steel. Lead is mainly, it will not allow these harmful radiations to go out. Okay, so that is why the nuclear reactors must be shielded with lead and steel walls so as to stop radiations from escaping to the environment. That's one thing. Second one, there must be backup cooling system. Last year also, even in 9th standard, you say in the nuclear power plant, saw that there should be a cooling system, because it gets heated so much, so that continuously it has to be cooled down. Okay, so backup cooling system should be there. Even if one system fails, even if one of the cooling system fails, the whole nuclear reactor can stop working. So it is so important that they'll have a lot of backups. Okay, recently there was a flood in Japan, in Fukushima. There is a nuclear reactor, and this was the problem. The cooling system, water entered into the cooling systems, and flood water entered, and the things got shut down, and they had to really restore the other ones faster. Otherwise, the whole thing would have destroyed. Okay, so it's so important to have backup cooling system. Third one, they should put on special lead lined aprons and lead gloves. The people who are working in the nuclear power plants, they should use lead lined aprons made of lead lining, and lead gloves. Okay, everything they have to have of lead. Okay, lead apron, lead gloves, and they have to use lead tongs. You know what are tongs? Yeah, chimta or whatever it is. And then I have written fourth point ka continuation. You can write this. And radioactive substances must be kept in thick lead container with a narrow opening. They have to keep in a thick lead container. Okay, everything should be of lead, children. Remember that. Lead apron, lead gloves, lead tongs, and lead containers with narrow opening. And the fifth, uh, and the fifth safety measure should be how we are disposing the nuclear waste. Okay, first of all, they kept in thick casks means, again, huge containers, and then they have to be buried in deep underground stores or buried in useless mines, and then these mines must be sealed after storing the casks. Okay, they have to take extra care to make sure it is dumped in a place very, very far away from human inhabitation, and that too in a very deep place, buried in useless mines, and mines have to be sealed also. Okay, now the last part is background radiation. Now this is a very interesting topic. You know what are background radiations? These are radiations. They are the radioactive radiations, alpha, beta, and gamma, to which we are all exposed to even in the absence of an actual radioactive source. The point is, you are all we are all exposed to some amount of radioactive radiation in our lifetime in this world. Some amount of We are all exposed to some amount of alpha, beta, and gamma radiations. That is called background radiation. From where do they come? What are their sources? There are two sources: internal source, external source. Now, internal source means from within our body. Doesn't it look amazing? Inside your body, there are some radioactive substances that can emit radiations. What are they? Potassium K40. This is radioactive. They are mild ones, but they do emit some radiations. Carbon C14, radium present inside the body. Okay, they present in our entire body and they affect all parts. While radium is largely found in bones, so it affects only the bones and the reproductive organs. Okay, so internal source inside our body. Remember, there are some radioactive substances that keep emitting some amount of radiations. The external source, you know it, cosmic rays, even the sun rays, that is falling sometimes have lots of gamma radiations. Cosmic rays, the rays coming from outer space. Naturally occurring radioactive elements such as radon 222 and solar radiations. These come from the external source. Okay, I've put good news. Okay, many children get scared when they heard this part, but there is a good news. It says it is very little amount. The radiations to which we are exposed to, the level is very less. It is not possible for us to keep ourselves away from the background radiation. But the total background radiation from both internal and external source do not exceed the permissible dose for human safety. So we need not worry about it. What a great way to finish the syllabus, finish this chapter and finish this syllabus. Okay, children. So you don't have to worry about background radiations, but they are there, to which all of us are exposed to, even in the absence of an actual radioactive source. Okay, don't forget this. Good news also that will keep us going. So with this, we've completed the syllabus for this year. Thank you so much for cooperating and watching all the videos patiently. See you later.